Hello, and welcome to CARLA AI's Summer Projects Showcase. Over the past couple of months, we've trained a car to drive itself using reinforcement learning. The simulation was done on CARLA, an open-source environment built in Unreal Engine 4. As you can see, the car kind of works, but it still has a long way to go. One of the main ideas in reinforcement learning is to value certain actions that the agent takes. In our case, the agent is the car itself. The actions it could possibly take are to drive, brake, and steer. For example, if the car moves left and bumps into a streetlight, it will get penalized. On the other hand, if the car goes straight and stays within its lane, it will be rewarded. It's possible to take an input image in from the CARLA simulation, encode it to a compressed format using convolution layers, and then estimate the reward for every possible action using a neural network. Such a structure is called a deep Q network, since the estimated rewards are mathematically derived using a Q-learning function, better known as the Bellman equation. The agent should be designed to take the action with the highest reward so it performs optimally. However, sometimes it may be necessary to take a random action, since a better unexplored option could exist. This way of choosing what actions to take is called epsilon greedy action selection. The class DQ network defines the structure of the neural network, including how many convolution layers it has, the inputs and outputs, and activation functions used. The class memory defines a buffer, which is a big array holding a bunch of experiences. An experience is an array made up of 4 elements: current state, next state, action, reward. When training the neural network, all of these are required to estimate reward and get randomly sampled from memory to help the car adapt to different driving conditions. The training function implements a target and evaluation network. Reinforcement learning, unlike other machine learning methods, uses 2 networks for training. The idea behind this is that the network's outputs, known as rewards, are estimated based on other estimates. This idea of using a guess to make another guess is called bootstrapping. It's hard to train a network when the target values keep changing. There's no fixed number to converge towards when optimizing, so the target network freezes its weights so its outputs do not change. The evaluation network will then train by comparing its changing reward estimates to the targets. The idea behind this is that with tons of samples, the evaluation network will figure out the optimal way to play. The training function will sample experiences from the memory buffer, compute target Q values using the Bellman equation, and compute loss and train the evaluation network. It'll continuously do this every time the car moves one step forward, so you can see how data-intensive things really get. Diving into how CARLA gets used is actually a lot easier. The CARLA simulation itself works using a server where data gets passed back and forth. The videos you see on your screen is a render ran locally using server data. To interface with the CARLA server, to get input images from the car, check for collisions and lane crossings, the sensors class was created. Of course, at the end, even after all this planning and work, we found out our model worked horribly. But we're looking into ways to improve its architecture, namely using actor-critic methods instead, and hopefully it can get some better results. Oh, by the way, the source code is available online if you want to dive into it. Of course, we like to give credit where it's due and want to thank authors Philippe Rosa and Thomas Simonini for their open source contributions, which the program is largely based off of.